Hi everybody, welcome back to the Feynman Technique. This is problem 2 off of the 1999 AP Calculus AB exam. This is the exam actually that I took. Uh, Again, didn't do very well on it my first time around because I was a little bit cocky. I didn't study for it. I thought I was too good to study, and I was wrong. This is a very difficult test, especially if it's your first time taking it. But anyway, this is the problem. So the shaded region R is bounded by the graph of y is equal to x squared and the line y is equal to 4. And that's pictured right here. So part A says find the area of R. Okay, this is just a quote unquote simple area problem. It's a definite integral and we're trying to find this. So how are we going to do that? Well, first we need to find out, what are we integrating with respect to? Are we going from left to right? Are we integrating with respect to x, or are we integrating with respect to y? Now, technically, you could do it either way. It'd be much generally in these problems you are integrating with respect to x. There are some volume problems where it might be easier to integrate with respect to y, but for these area problems, you generally want to integrate with respect to x. So let's just start by putting down our integral sign and then a dx because we are going to be integrating with respect to x. Now we need to find our bounds of integration because this is going to be a definite integral. We want a definite answer, like an actual answer. We don't want to get an equation back, so it's going to be a definite integral. What are our bounds going to be? Well, we can see our bounds are going to go from here to here. We need to find out what the x value is at this point and this point. And that can be found by setting these two equations, this y is equal to x squared, that's this thing right here, and this line y is equal to 4, and setting them equal to each other. So if we do that, if we say x squared is equal to 4, then we get that x is equal to plus or minus 2. So this would be our x is equal to minus 2. This would be our x is equal to 2. So we have the integral going from minus 2 up to 2. All right. Now what are we integrating? We're trying to find the area of this. So always remember when you are trying to find an area, you divide this thing up into a bunch of little teeny tiny, well, very not teeny tiny, but very thin rectangles. You're adding this rectangle up, this rectangle, this rectangle, this rectangle, all the way through. So you have a bunch of little rectangles varying in size. The height of each rectangle is going to be the distance from here to here. What is the distance from here to here? It is 4 minus f of x. And I'll say that this is also f of x. Okay. So again, what is the distance? It is 4 minus f of x. And we are adding up a bunch of them from negative 2 to 2. So let's just write that down as is. So we have 4 minus f of x. And that is the height of each one of our rectangles. And that's the height. And our width, what is the width? Our width is dx. It's an infinitesimal width, and we are adding up an infinite number of them from negative 2 to 2. I know I kind of over-explained this. Most of you watching this probably could do this first part very, very easily, but I am going to be over-explaining a lot of these things because I believe the explanations that they give on the College Board website are not sufficient for somebody that's struggling with it. So, anyway, this is our equation. Okay, well, what is f of x? F of x is x squared. Okay, so let's just put that in there. All right, and what's that equal to? Well, I just said I was going to over-explain things a lot. I'm actually not going to be over-explaining this. Once you get to here, anybody watching this video should be able to solve that integral. If you're having trouble with this sort of thing, like if this was just presented to you on a test and you're having trouble with that, either start studying really hard or maybe rethink taking the AP Calculus test for now until you get comfortable doing stuff like that. You should be able to crush definite integrals like that. You should be very comfortable with taking all sorts of derivatives. You should be familiar with trig sub, u sub. I'm not sure if they expect you to know integration by parts. I don't think they do, but you should definitely be able to solve this integral, no problem. So I'm not going to be going through the steps. That's equal to 32 over 2 units. And that is the answer to part A. So let's leave that on the board for now and move on to part B. Now it says find the volume of the solid generated by revolving this thing around the x-axis. Okay, how are we going to do that? Well, what does this mean? Find the volume of the solid generated by revolving r about the x-axis. A lot of you probably were fed a bunch of formulas for solving this, and that's good. But on this channel, I'm going to explain where this comes from. So, we're taking this region right here, and we're sweeping it around this line to sweep out a solid. And you can kind of see what it's going to look like. You can kind of picture in your head what it's going to look like. It's going to, well, I don't know exactly what shape that would, what 3D shape that would be called, but you can see it. It's going to form a solid area. So how are we going to figure out what that solid area, or volume, sorry, is equal to? Well, let's take the same idea. We're going to split this up into a bunch of rectangles again, and then sweep each one of those rectangles around the x-axis. And what's that going to give us? Well, it's going to give us a ring that kind of looks like this. I apologize for my bad circles if they turn out to be bad, but it's going to look something like that. This is basically the height of one of the rectangles. That's this height right here. From here to here. You can see this is a ring. It has an inner radius. This inner radius is represented by this part right here. That's the area we're not taking. This outer radius is equal to from here to here. So we have the outer radius going from here to here. That's here to here. And then the inner radius going from here to here. And we're doing an infinite number of them with an incredibly small height this time. We're going to have an actual height to this ring. Or washer, however, whatever your professor has told you to call it. This is either the ring or the washer method. We'll say washer. I think that's more common. So we're adding up a bunch of these washers. What is the volume of a washer? The volume of a washer can be given by this. Oh no, my pen's running out. The volume of a washer is given by pi times the outer radius. We'll call that r sub o minus the inner radius. We'll call that r sub I. Squared and squared. And you can see it's, oh, and then times a height. And we can see that this is just the equation for basically two circles, and we're subtracting them. We have pi r squared, outer radius, pi times the outer radius squared, that's the area of the big circle, minus pi times the inner radius squared, that's the area of the small circle. Then we're multiplying them both by pi. And then we're multiplying them by h. Okay. So let's fill in the pieces here. Don't forget, this is just the area or the volume of one of our little tiny washers. Or very thin washers, I should say. So let's start filling in these pieces. What is our outer radius actually equal to? Well, what does it correspond to on our picture? Our outer radius is always going to be 4. This is always going to be our outer radius, the distance from here to here. That's always our outer radius. So we can say the outer radius is 4. Now, what is our inner radius? That's the distance from here to here. Well, what is that? That's just f of x, or x squared. So our inner radius is always going to be x squared. Now, what's our height? What's the height of each one of these washers? Don't forget, this is the radius. This is the inner radius. And then our height is going to be the distance from here to here, which, when we're talking about integration, that is a change in x or dx. So our height is dx. All right, and we are integrating this from -2 to 2. All right, so we kind of already have this set up over here. Let's use that. We know we're going from -2 to 2, and then we're going to be integrating this thing. All right, well, it's definitely going to have a factor of pi, so we'll just bring that pi right outside the entire integral. I hope you're all comfortable with that. And then we have this thing, our outer radius squared. Our outer radius is 4. Squaring that will give us 16. Minus our inner radius squared. Our inner radius is x squared. X squared squared is x to the 4th. Times our height, we already have it, that's dx. And again, this is not something that I'm going to be explaining how to do. That's a simple, I mean, there's some calculation to it. There's room for mistakes. Just don't make them. Don't make sign errors. You know, don't do any of that stuff that you've been told not to do, basically. But anyway, what you get if you evaluate that, you take the antiderivative, which is 16x minus x to the 5th over 5, and then you evaluate it at the bounds and multiply it by pi. And what you'll get is this. 51.2 pi, or roughly 160.85. And they like it to 3 decimal places, so we'll say 850. All right. And I believe that is it for part B. Find the volume of the solid generated by revolving R. Okay, well, we should say units also. They don't specify what the unit is, so just say units if you want to be sure of getting full credit for it. Okay. So, now what do we have? Part C. And I say, in this I said C description because it's, I'm going to put part C, the actual text of it, in the description to this video. And also I will link to the actual problem on the College Board website. But this is what it says. Okay. So there exists a number k greater than 4, such that when r is revolved about the line y is equal to k, the resulting solid has the same volume as the solid in part B. It has this volume. Aha. We're talking about volume, so it better be units cubed. Yeah. Has the same volume as the solid from in part B. Right, but do not solve an equation involving an integral expression that can be used to find the value of k. All right, so let's read that one more time. There exists a number k greater than 4 such that when r is revolved about the line y is equal to k. So we're talking about some line that's up here. Y is equal to k greater than 4. So we have some line up here. And then we take the same solid, or the same area, the same region, and we take it and we revolve it around that line. We don't know what k is. We want to make k so that when you revolve that thing around the line y is equal to k, you get 51.2 pi. All right, so we're going to use basically the same method. We're going to use the washer method, but what our outer and inner radiuses are they're gonna change based on this. So we have this line y is equal to k. We revolve this region around it. What is our outer radius? Well, the bigger circle, the bigger of the radiuses is always going to be the distance from this line y is equal to k to our function x squared. So in this case, our outer radius is going to be, well, k from 0 to k minus, it's going to be this distance from the line, from the x-axis to the line y is equal to k, minus this distance. That's always going to be the outer radius. From here to here, from here to here, from here to here. So we have our outer radius being k minus f of x. What is f of x? It is x squared. What is our inner radius going to be? Well, our inner radius is always going to be the distance from y is equal to k to y is equal to 4. So it's going to be from here to here, from here to here. It's always going to be the same thing. That thing is going to be k minus 4. I hope you can see that. K minus 4. And I will get a new, I'll get a new marker for my next video. I know this might be a little bit hard to see. It's running out of ink. So our inner radius is k minus 4. And what's our height? Our height's still the same thing. Our height is just a very small change in x. So this is our formula right here. Okay, so what do we want? Well, first of all, let's set up what the volume of this thing is going to be. What the volume you get by revolving this around the line y is equal to k. What's that going to be? It's going to be the same setup as this. We're going to get pi times the integral from negative 2 to 2. But now we're going to have something different in here. We're still going to have our outer radius squared. So we're going to have our outer radius squared. What is our outer radius? It is k minus x squared. Then minus our inner radius squared. So minus something squared. Our inner radius is k minus 4. Okay. And let's put some square brackets around that. And then, of course, we have times our height. Our height is dx again. Okay, so we have this. This is, in terms of k, that's going to be the volume of our solid for any value of k. Basically, if we revolve that around the line y is equal to k, This integral expression gives you the volume. That's what you would get. So we could make k negative, we could make it positive, we could make it whatever we wanted, and the volume of it would be given by this expression. But what does the question say? It says, write but do not solve an equation involving an integral expression that can be used to find the value of k. What do we want this whole thing to be equal to? We want it to be equal to the same thing as we got in part B, which is this. We want it to be equal to 51.2 pi units cubed. So we set it equal to 51.2 pi, and we're done. This is an equation involving an integral expression that can be used to find the value of k. We would evaluate this integral. It might be difficult. That this is kind of messy, but you could do it. And then you'd evaluate it. You'd set it equal to 51.2 pi and solve for k. And we are looking for a k value greater than 4, and it is a good thing that they said, write but do not solve an equation, because guess what? There is no such value k greater than 4 that satisfies this equation. There is only one solution for k to this equation, and it is approximately k is equal to 3.43. That's actually the only value for k that would satisfy this equation. So when I originally took this, I wasted a lot of time trying to find the value for k that's greater than 4 that satisfies this. And I did that because, you know, I didn't read the problem carefully. It says write but do not solve an equation involving the integral expression that can be used to find the value of k. I was done once I got here. I didn't need to waste the 15 minutes it took to actually try to solve this and then go back and try to resolve it thinking I had made a mistake because I didn't get an answer greater than 4. So the lesson there is definitely read the questions carefully, because once you get to here, you're done. There is no k greater than 4 that satisfies that equation. All right, so that's it. That's part A, B, and C of question 2 on the 1999 AP Calculus AB exam. Hope you enjoyed that, and we'll see you next time.